Okay, so we are in ECE3200, Introduction to Semiconductor Physics. So those of you who are in the wrong class, take note, I guess. Okay, so today we're going to just go through some logistics in the first chapter. I'll talk a little bit about grading and so on. As you noticed, I'm trying to record the slides. Unfortunately, the microphone was not working, so we're going to have to use the internal microphone, which may not be very good. But I'll post them online, so you can watch them at your own pace and all that. This is sort of important because we're going to go through lots of concepts pretty fast. So I'd suggest that you go back home, take a look at it, slow it down, stop where you want. That's the nice thing about the recordings. Hopefully it'll work out. Let me know if you have any comments. Okay, let's get started with the logistics. So my name is Rajesh Menon. I'm a professor in the electrical and computer engineering department here. So the most important things to remember for the class, the course website. So everything will be posted there, including all the notes, problem sets, not the quiz, but anything else, all the slides and all that stuff. I'll show you in a minute how to access it. So we'll meet Tuesdays and Thursdays, 9 to 10:30, 9:10 to 10:30. I'll have an office hour on Wednesdays, 1:30 to 2:30. My office is in MEB 2256, just the building next door. However, I have to say that you really should be emailing the TA first, unless you have some serious concerns. So let's first look at the website so you can access everything. Okay, so I'm going to show you very quickly. You go here. So it's lons.utah.edu. And if you go to the courses, so you can see the courses, and there are two there, but just go to the first one, 3200. And everything's there. Okay? So the basic information about the class, today's class, and I posted a bunch of videos on some background information that you may want to look at. And I suggest you look at them because we're not going to be able to cover a lot of the detail. So I put a whole host of things which I thought were useful, mostly videos. And I'm going to post the slides as well, and Thursday and so on, and the schedules there as well. Also, you can leave, if you have questions, comments, you can also post them. I'll take a look at them. That might be a more efficient way to do it, but whatever you guys want to do. Okay. So that's the basic stuff. Let's go back here. Okay. Perhaps the most important person you need to be aware of is Nitin. Nitin Bhargava is here. So if you have any questions with regard to grades, problem sets, concepts, you need to email this email address. So not me. Because the email might go into the spam folder. So don't email me quite yet, unless it's something very serious. So feel free. But teach3200@gmail.com. One of us will respond. Okay? So those are the two important things for logistics that you should be aware of. This email address and the website. Okay. Now, in addition to the lectures, one thing I have noticed when I took this class long time ago, actually, not here, but the equivalent class, I realized that the way to learn these concepts is actually to do some problems, because a lot of the concepts as an engineer can be very abstract. The abstraction is important because that's how you formulate the problems mathematically and so on. That's important to understand, but that's not enough to really understand what's going on. So you have to actually do the problems. So this is the reason I suggest you attend the review sessions as well. Now, the review sessions are not mandatory. They're recommended, and Nitin will be leading them. They'll be Mondays and Fridays, so you have two options, and they'll be the same, so you don't need to come to both, unless you want to, it's fine. 5 to 6 p.m. in that room, WBL 112. So the three goals to the review sessions. First is to answer your questions if you have, conceptual questions, whatever. Make sure you bring them and ask them and discuss them, okay? The second is to if you have questions about problem sets and so on, of course, he's not going to solve them for you, but if you have fundamental questions. And the third thing is to practice problems. So he's going to work through several problems. Okay? And this is actually useful in my experience, so that's why I would suggest you do it. Okay. Those are the basic logistics. Okay, so that's the text. This is it. Solid-state electronic devices, 6th edition. This is perhaps the most common textbook around the country for this kind of a class. And it is actually written by two fairly well-known scientists in the field, Ben Street and Sanjay Banerjee, and I know both of them. They are professors at the University of Texas in Austin. They're actually doing research in this field, so they're very comprehensive textbook. So it's a useful book to have as a reference if you're interested, but it's also on reserve at the library, so you don't actually have to buy it if you don't want to. But I'm going to follow the book fairly closely, which is an advantage for you because you can kind of see where we're going to go, and so read up before you come to the class, and look at the problem sets, examples, things like that, and if there are any new things, I'll actually provide. Mostly on the web. I'll post them so you can take a look, or I'll show them here. Okay? Okay, that's... okay, grading. This is probably what you're most interested in. Very simple, and I'll probably stick to this. Only 3 things that matter, the grading. Problem sets. They count for about 1/3 of the grade. There will be about 7 of them. I'm not entirely certain exactly how much. You will have about 2 weeks to finish them, so it'll be long. Okay, so I think the next one will start on Tuesday. So the first one will start on Tuesday. And he'll post them online, and I'll show you also. Okay, so you'll have 2 weeks to submit. The important thing is you cannot be late. You will lose points, 1 per day, roughly. Okay, so it's very important. 2 weeks should be enough for you to do it. The next important point is that collaboration is encouraged. So feel free to talk to your friends. Discuss with them. Try to do them together, which is fine. It's important. In fact, I would encourage it. But of course, don't plagiarize. We will find out. Obviously, we can look at them and see. It's not a huge class. It's pretty easy to tell. So try not to plagiarize because it's important. Right? Try to do it yourself. The goal here is not for you to get A grade or A+ or C or whatever. It's for you to learn. Right? So if you don't do it yourself, you're not going to learn. I can guarantee you that if you don't do it. By just coming to the lectures, you won't learn the concepts. You have to actually do them. Okay, the second point for grading is the midterm. And I'm giving you plenty of notice. It's on March 7th, 9 to 10, at the same time as the class. Probably an hour, maybe a bit more than an hour. We'll see. Okay? It'll count for 1/3 of the grade, and the final count for 1/3 of the grade, which I don't remember, but it's in the week of April 29th. I don't remember the date. But I'll remind you when I find out. Okay. So that's grading. Pretty straightforward. Okay. So I'm pulling these slides from the web, so unfortunately it might take us some time. I thought I had loaded them before. So for the important images, I'll stop. I guess this is not terribly important. So the objective of the class is primarily to understand the fundamental mechanisms of solid-state electronics. So how do chips work? And of course, electronics is very important because it's ubiquitous in our life today, right? So everything that we do, like computers, iPads, phones, whatever. Not just that, but if you were paying attention to the Consumer Electronics Show, which is going on this week, you will notice that electronics is becoming ubiquitous in anything. So I think the story I read, I don't know if you nodded your head, but was the microprocessor in an oven or something like that, which apparently can control, increase the efficiency of the oven and make you a better cook or whatever. You can have it in a laundromat, a washing machine, and so on. In any case, it's pretty obvious that the future, we are going to have a very big proliferation of these kinds of devices. So in a sense, understanding the fundamental basis of where these devices come from or how they operate will serve you good in perhaps 2 or more ways. First, it will help you understand the current state of the technology and what has happened in the last, I would say, six, seven decades now. And of course, that will help you work in the industry today if you care to. Perhaps more importantly, it will also allow you to understand what's coming next, because this is a very exciting time for this industry, because there's a lot of change happening. You're hitting the limits of lithography in silicon, and then new kinds of devices are coming in, but they're all based on the same kind of physics, the fundamental solid-state physics and quantum mechanics and so on, which we will talk about. Okay, let me make sure this is connected to the internet. Oops. Hang on a second. Okay, I'm going to try that one. Turns that works faster. Okay, so yeah, okay. So hopefully that'll help. Okay, we can keep going. Let's see what happens. Okay, the schedule for the class. So I have kind of mapped this out, but it's a tentative schedule because things, we might slow down. Most likely, that's what happens in general. But as you can see, I'm going to follow the text fairly closely. So I would recommend that you read up. And it's a fairly well-written text. Some parts are kind of verbose and hard to understand, but I would suggest you to kind of at least attempt it. Today and Thursday, we'll go through chapters 1 and 2, which is actually a really a lot of topics, actually. So we're going to just skim the surface, because this is basically everything to do with crystal structure and applied quantum mechanics, which by itself is a course in itself. So we will just really touch the surface. So I recommend you to do your own reading if you're interested in this. Next week, we'll go to chapter 3, band theory, how electrons and charge carriers, electrons and holes, behave within semiconductors, which of course is the basis for all kinds of transistors, switches, and all that stuff. We'll go to the currents in semiconductors, PN junctions. PN junction is a basic device which is used in everything, transistors to solar cells. So we'll kind of spend a bit of time on that. Metal semiconductor junctions are slightly different. Then we'll look at simple devices and circuits. Then we have the midterm on week 9, which is March 7th, and then we have spring break. Then we continue with chapter 6, basically the most popular device today, the metal oxide semiconductor transistors. So we'll talk about the physics and the device models and so on. And finally, we'll look at bipolar junction transistors, which are much faster, and they're fairly more specialized, but they're important to understand as well. Then we have finals on week 17. So fairly straightforward in terms of progression. So I would recommend you take a look at the book. Again, that will help you understand a lot of the details. Okay, I have to somehow make these things load. So I want to try this again. Okay, that's better. Okay, I gotta skip through all this again. Okay, so we'll spend a few minutes understanding the motivation, basically diving into what I just mentioned. So first of all, some of you have probably seen this. This is a graph which shows the evolution of microprocessor technology. So on the horizontal axis is our years, and the vertical axis is the MIPS per $1,000, which are millions of instructions per second per $1,000. So for $1,000, how fast of a computer can you buy, basically? So you can see a bit more than 100 years ago, we had mechanical calculators, which are equivalent, a little bit faster than manual calculation, probably, something like that. And we have pretty much an exponential curve, because you can see this is a logarithmic scale, right? So this is million, thousand, so 3 orders of magnitude. Each line represents 3 orders of magnitude, and it's a linear line, so it's a log scale. It's evolution, exponential increase of performance. We are about here, right, 2013 or so. So this is a few years old, but the trend is clearly in this direction. There is a lot of talk on saturation of this trend because of lithography limitations, I will mention, because that's part of my research. But it's pretty clear to most observers that that's continuing to increase. And it's illustrative to look at the equivalent brain equivalent. So you can see we are now in the order of about a lizard brain connections, and in terms of instructions per second. And of course, tending towards artificial intelligence to some extent. In any case, what has enabled this sort of very dramatic evolution is actually solid-state technology. Because up to down here, this is kind of where the solid-state technology came into being. Until here, they were all either mechanical or vacuum electronics. Okay, so you might have seen in your history books, we had something called an ENIAC, which would fill a room about as big as this, but be able to do, simple calculations. The military used to use this primarily to calculate the trajectories of missiles and rockets and things like that, as well as for cryptography. Okay, but you can see it's not very practical. Now we have the same computing power as something like this. Okay, and that is the dramatic change that has been enabled by electronics, microelectronics. Now, to look at this more, to understand why this has happened, is very straightforward. If you look at the electronics that went into the ENIAC, the old machine that I showed you before, they were all driven by vacuum tubes. So these are all switches. So each one of this is basically a vacuum tube transistor, which is typically a switch, just like the transistor that you have in your integrated circuits today. But they're all discrete. They're big. They're huge. So if you want to have billions of these, you take up a lot of room, and they're slow and all that kind of stuff. They take up a lot of power, so it gets very hot. So it's not very useful. But this transition basically summarizes what has happened in the last 60 years or so. Okay? We've gone from a very discrete transistor device to a fully integrated device. Something as small as that now has the functionality of all of this stuff. I mean, much more than this stuff. You have billions of transistors which go in here. Here you can see you have about 10 or 20. Right? So you have like 6 orders of magnitude more performance in something like 2 orders of magnitude smaller area. That's a pretty dramatic change. I don't know of any other industry which has undergone this kind of evolution. Okay, so if you look inside the microchip, what you see is basically something which looks like this if you open it up. Okay, if you open up your pen, this is, I believe it's one of the Intel processors. I forget which one. It looks like this. Basically, you have all kinds of electrodes on the sides, and you have switches inside. So you have all kinds of circuits in here, which is similar to what you learned in your signals and circuits class. I don't know exactly which classes you take here. Sorry, I'm not from here. So the circuits are designed on here, and each of the individual switches are also in here. And they kind of look like this at the nanoscale, okay, at the most advanced scale. So what you're looking at here, is essentially what's called a transmission electron micrograph of a transistor. Okay, that's 30 nanometers across. This is silicon, and this is polysilicon. And these dark regions are also silicon, but they're doped, as we'll talk about later on. Okay, and this is a switch, so the electrons flow across here. But this is only 30 nanometers. Now, 30 nanometers means 30 times 10 raised to minus 9 meters. Okay, 10 raised to minus 9, so you can imagine that's pretty small. So this is about, I would say, about a few hundred atoms wide. It's pretty small. This is the fundamental reason that we are able to do that integration. The fact that we can make these kinds of devices in a reproducible, cost-effective manner. So keep that in mind, because we won't actually touch this. We're going to talk about how it works. But this is the reason why it is so ubiquitous today. This is done by a process called lithography, which is what I mentioned before. Okay? So one of the fundamental limitations the industry is running into is how do you make these smaller? So the reason to make this so small is because you can pack more devices together, right? If you make them small, you can put more of them in the same area, which is this integration approach. But if you're down to about 100 atoms or whatever, 150 atoms, how much smaller can you go? Can you go to 10 atoms? Can you go to 1 atom? And these are the fundamental limitations and questions that are being asked today. So when you kind of think about this class, you should also think about where those questions can lead us to some extent. And I'll try to highlight important areas there. Okay, so with that idea in mind, hopefully you'll agree that this is a useful class to learn, to understand some of these basic principles, okay? which has enables its evolution, and perhaps you will be part of this part of the evolution going further on. Okay, now the chapter 1 for the text deals with primarily the materials, the very fundamental materials involved in microelectronics, which are semiconductors. Okay, it's a semiconductor device physics class, so we have to talk about semiconductors. Now, if you look at the periodic table, semiconductors are over here, shown in the pink. Okay, silicon, germanium, antimony, arsenic, and so on. Okay, these are the elemental semiconductors on column 4. Okay, silicon and germanium are the most common ones. Okay, silicon is obviously the most common one. Germanium is used for some very specialized devices. Okay, and we will see why semiconductors are important in a second. There are also other kinds of semiconductors where you can have compound semiconductors, where you use 2 elements to form semiconductors. So instead, the most common one is gallium and arsenic, Ga and As. If you put them together, you get gallium arsenide. Now, gallium arsenide is very, very important, primarily for LEDs. So light-emitting diodes, all kinds of optoelectronic devices. So everything that drives the internet, for instance, with fiber optics, is based on laser diodes. So all of that is driven by, not gallium arsenide in particular, but these kinds of compound semiconductors. You can also have gallium phosphide and gallium nitride. Those are very important for visible LEDs, clearly very important for lighting in the future. Again, it's not just microprocessors, it's also other applications as well. Although we won't really dwell too much on the optoelectronics part of these devices. You can also have, gallium arsenide is very important for solar cells. That's the other application. And I'll talk very briefly about that also. Okay? Although it's not really the emphasis of this class. You can also have more combinations. So you can have things like gallium, aluminum, arsenide. Okay? And you will see why these are useful, because different materials provide different energy band gaps. And by combining them, you can control the band gaps, and which allows you to control how electrons behave in the material. Okay? And that can have very big impact on the macroscopic properties, like what color of light comes out of the LED. Can be controlled by controlling the concentration of aluminum in gallium aluminum arsenide, for instance. Okay? So there's lots of very, very interesting engineering that happens. You can also, of course, combine more than 3. You can have 4. Okay, it's much more difficult to do, but you can, to give you more flexibility in your design of your materials. Now, why are semiconductors important? They're very important because unlike metals, which are good conductors of electricity, and unlike insulators, which are poor conductors of electricity, semiconductors are average conductors of electricity, typically poor. But the advantage is that you can control their conductivity very dramatically. You can make them insulators, or you can make them metals, pretty much, by a variety of techniques, and we'll talk about some of them, primarily by doping. Okay? You can also control the optical properties, like I said, by putting different materials together. So if you want a red LED versus a blue LED, okay, things like that. One example of this control is shown here, where you have a lattice of silicon atoms. Okay, there's a silicon. And of course, this should have been silicon, but now we have removed a silicon atom and replaced it with an antimony atom. Okay? Now, antimony has an extra electron compared to silicon, the outside shell, the outermost shell of electrons. Okay, so you have an extra electron that's now hanging around. This extra electron essentially contributes to extra conduction. So it makes silicon, one antimony atom in a few million silicon atoms can make a huge difference in the conductivity of silicon. So this approach of being able to control the conductivity, now you can see a switch, right? You're either an insulator or you're a conductor. That's a switch. Right? So this is one very, very basic, simple example, and we'll come back to this. Okay? A very small percentage of impurities can make a dramatic difference, and this motivates us to really understand how this happens, why this happens, how we can engineer this. We need to really understand crystal structure. Okay? So in the rest of the class, we're going to talk about crystal structure, which is actually a course in its own merit, but we really don't have the time to delve into it. So I will post whatever I posted online and and the notes in the text. Make sure you try to read through them to really understand the concepts, because some of them are fairly abstract. If you are not a very geometric person, you can think in 3 dimensions, which I can't, so I find it hard. So what are crystals? Okay, so matter exists primarily in many forms, but let's say for our purposes, 3 forms. Okay, it's either crystalline, it's amorphous, or polycrystalline. Now, what does crystalline mean? Crystalline means that the atoms are arranged in a periodic lattice, very nicely ordered. So you can see it forms a nice periodic array. Okay, what's amorphous? It's random. The atoms are not periodic; they're kind of randomly arranged. Very simple concept. You can have something in between, which is polycrystalline, which means that you have small regions where the atoms are arranged in a periodic fashion, but outside that region, the periodicity could be different, the orientation could be different. So you basically take a whole bunch of little crystals and put them together, that's polycrystalline. Okay? And all of these are important in semiconductor electronics. Okay? Of course, crystalline silicon is probably the most important one, but all of these are equally important, as we will see in the rest of the class. Okay? So that's a basic, as an example of these materials, crystalline materials are silicon. Okay, that's the obvious one. Quartz, diamond, things like that. Amorphous materials are glass, glasses. Almost all glasses are amorphous silicon dioxide. And all kinds of metals could be amorphous as well. Polycrystalline materials, the examples are, for instance, sand. Silicon dioxide in the form of sand is polycrystalline. Silicon, some kinds of silicon can be polycrystalline. So any crystals can be polycrystalline if you lose long-range order, right? If you don't have the long-range periodicity. So it's the same kind of materials. And they're all solids. That's the other example. Now, crystals are defined, of course, by the fact that the atoms are periodic. Okay? Now, you can, in a periodic set of atoms, you can define certain basic terms to talk about crystals. And that's what we want to define first. The first thing is the unit cell. So because it's a periodic distribution of points, we know any periodic function can be defined by what the portion of the function that's periodic, that's repeated, right? It's exactly the same way in geometry. So you have this region, in this example, you have a rhombus formed by ODEF. That's basically repeated across, right? Translated in this 2D crystal. Okay? And you can think of this blue portion of the rhombus as the unit cell. That's repeated. Okay, so that's the definition of the unit cell. It is the simplest repeating unit, and not necessarily the smallest. For instance, you can have more than, in a same lattice structure, you can have different unit cells, right? So for instance, in this example, you have the rhombus. This rhombus is the same as that rhombus, right? It's all periodic. Now, by the way, do you see the advantage of the unit cell is that if you know the properties of one unit cell, you can define the properties of any other unit cell. Because they're all equivalent, right? They're periodically repeated, except at the boundaries, which are very special. We'll talk about that later. Okay? Now, what I meant to say was that the unit cell is not unique. You can define unit cells in a variety of different ways. The very simple example is shown here. This rectangle here can be a unit cell as well. PQRS with T in the center. It's a face-centered rectangle. You have your atom in the center. And you can see that whole thing can repeat as well. Okay, if you actually try it. So that can be a unit cell as well. Sometimes it's easier to deal with rectangles than with rhombus because the angles are 90 degrees. So sometimes we prefer to do it with the rectangle, so even though it's a larger unit cell. So again, all of these are, I don't expect you to memorize them, but just make sure you're aware of these terms and what they actually mean conceptually. Okay? Essentially, it allows this definition of these terms allows us to analyze the properties of the crystal. That's why we need to understand them. Okay? And in particular, we're interested in the behavior of electrons in the crystal, which we will come to next week when we talk about band structures. Okay, the few other terms that you should be aware of are the primitive vectors. So in this case, you have a vector here, A, and you have a vector here, B, that define the entire unit cell. Right? And for this rhombus, you only need these two vectors. And anything that repeats as an integer multiple of these vectors, like this R, represents another unit cell. You see that? So this is the origin. If you have a vector, if you translate the unit cell by an integer multiple of A and B in their respective axes, you form another unit cell. Okay? So try to visualize that, because we'll get to a much more complicated geometry very soon. So this is a two-dimensional geometry. It should be relatively easy to visualize. Right? Okay. In nature, of course, is three-dimensional, not 2D as we drew. So we have all kinds of other lattices. In fact, there are 16 types of lattices, which we actually won't cover. And there's a lot of very, very interesting mathematics which define all this stuff. In fact, it's a whole class, graduate level class for this. So we'll really touch the surface here. We have what's called a simple cubic lattice, which is the simplest possible lattice. You have a cube, an atom at every corner of the cube, and you repeat that cube. Very straightforward. That's sodium chloride, salt. That's the lattice. Okay. You can have a body-centered cubic lattice, okay, where it's exactly the same as the simple cube, except that now you have an atom in the center of the volume, body of the cube. It's body-centered cubic, BCC. Okay. Then you can have, if you introduce more complexity, you can have a face-centered cubic, which essentially means that you have the 6 faces of the cube, and in the center of each of the face, you have an atom. Okay, do you see that in the picture? Okay, that's a face-centered cubic. FCC. That's a very common lattice as well, and we'll come back to that. In fact, a combination of two FCC lattices is the most important lattice, which we'll talk about next, the lattice structure for diamond and for silicon, which is why it's important. The silicon is by far the most common semiconductor material out there. So if you understand silicon well enough, you can probably understand most of the devices. Okay. Of course, I mentioned that each of these points here represent atoms, right? So this is kind of a simplified picture of reality, right? Atoms are not this small compared to the lattice. They're typically closely packed, especially in solids. So this shows most of the solid is space, right? Nothing in there. That's really not true. The atoms are packed typically as closely as possible. And of course, the atoms are held together, by the way, just to be clear, by either covalent bonds, right? That you might have learned from your freshman chemistry, or it can be electrostatic forces, like sodium chloride, right? Or metals and so on. Okay? Those you should have seen before in your freshman chemistry. So the packing of atoms sort of looks like this. You have a bunch of big balls basically packed together. And remember, these represent the points of the lattice. So in this example, can someone tell me what this particular one is? Yeah, it's a face center. Simple, right? So you can see an atom at, it's taking a cut through it, but you can see an atom at every corner and in the center of the face. You can't see the middle, but it's the face center. Okay? And you can figure out the geometric dimensions very easily, right? So if your A is the lattice constant, remember that is the dimension that's repeated, then you can very easily define this thing as A over 2. And if this is A over 2 as well, this is, using the Pythagoras theorem, the square root of A over 2 squared, square root of A over 2 squared plus A over 2 squared, which is just A over root 2. Right? That gives you, now what is this, why is this distance important? Do you see that? That is the distance between, the closest distance between the atoms. Right? It's not A, right? A has a little bit of space here, but this is the closest distance where they're actually touching, at least in this very coarse model. We'll change this model on Thursday. But, okay? So that's important. That number is the closest packing that you can get of atoms. Now, why is this important? Because that determines the atomic density, right? How many atoms can actually fit in a particular crystal. Now, you can see one very important concept here. The atomic density is different with direction, right? You look in this direction, they're very closely packed. Whereas if you look in this direction, they're not so closely packed. You see that? What does that mean? That means that the material properties of the material can change with direction. This will become important later on. It's stronger in one direction than the other direction. So for those of you who might have played with quartz, if you try to break quartz, they usually tend to break along certain directions. You get a very atomically smooth, so if you take a rock with some mica or quartz in it, if you break it, you will see a very clean cut. And that's because it is cutting through those directions which are weak in the crystal structure, like this, or orthogonal to this in this particular case. Okay, so, and you can also have differences in the optical properties. The speed of light in one direction could be different than in the other direction, which turns out to be a very important thing for optics. Okay, so just be aware of why we are trying to understand this so well, because it affects a lot of things as we keep going. Ah, okay, this is good. So this is actually an example for you. So first, I ask you to partner with someone sitting next to you, if you can, and discuss this problem. Just two, or if you're alone, find someone else, and talk about this problem for like 30 seconds or so. So first, let's look at the problem. First, introduce yourself to your partner. Left or right? Okay, let's look at the geometry. So first of all, how do we address this? Straightforward, right? You draw the BCC structure. So I want to draw that. Okay, I actually have the solution, I suppose. But let's go through it. So that's a BCC structure. To get the nearest neighbor distance, of course, we need to do some geometry. I'm going to point here because this one will be recorded. This will be so. This is the A, and that's A, so you can know what that distance is, right? Square root 2A. And then you know that's A, and then you know what that distance is. That's it, right? Half of that is the nearest neighbor distance. Okay? Simple geometry, but you need to visualize it. Of course, it can be a very complicated geometry, because we will make it very soon, but make sure you're clear on this. Is that okay? I'll repeat this very quickly. So you have A, right? So you can find this red line with Pythagoras theorem. Then once knowing this and that, you can calculate that, which is the diagonal across the body of the cube, right? And half of that is the distance between the atoms, the nearest atoms, right? Okay. So, yes?
So is the distance between the atoms, is that the packing fraction?
No, not yet. That's the next step. Sorry. We need to know the distance between the atoms to know the packing fraction. That's correct.
Okay.
Yeah, good point. I forgot about that. So, the separation between the nearest atoms you can calculate for 5 angstroms. This becomes about 4.33 angstroms. Now, angstroms is the unit, which is a tenth of a nanometer. Okay? About half an angstrom is the size of a hydrogen atom, as we will see on Thursday. So it's pretty small. Okay. So the radius of each atom is that. Volume of each atom is, of course, 4 by 3 pi r cubed, assuming it's a simple sphere. Okay. The number of atoms per cube. Okay, this is kind of important. So we have a cube which gets repeated. How many atoms are actually there? If I count them, 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9. But of course, only one actually fully belongs to the cube, right? Everything else is shared. So the total number is actually 2, it turns out, because each of the corner atoms are shared between 8 different lattices around it. So you have to only count it 1/8. So remember in that the cutoff view, you only saw 1/8. Okay? So you have 2. So the packing fraction is how many atoms are there per unit volume. Take the number of atoms, which is 2, divided by the volume of the lattice. Sorry, it's actually my mistake. It's the packing fraction is the total volume occupied by the atoms, so 2 times the volume of an atom, divided by the total volume of the cube. So that represents how closely, how densely are the atoms filling the cube, essentially. Yes?
How do we know the radius of the atom? Like, where did that actually come from? I understand what it's representing, but I don't remember.
Actually, that shouldn't, my mistake. That shouldn't be the radius of the atom. That should be half the distance between. So the assumption.
So that's the separation of the atoms.
That's half the distance between the nearest neighbors.
Okay,
See the whole.
that makes sense.
So now I recall. When I put this together, the assumption is that they are basically spheres touching each other. The nearest neighbors are touching. Obviously, that's not the right picture of an atom, as we will talk about on Thursday. Okay, but do you see what's happening? Again, I should point here. So this distance is twice the radius of the atom. That's the assumption here, because you have 2 cubes, two spheres basically touching. You see that? Okay. That's why it's the radius of the atom. Again, very, very simplistic model. Not true. But it's useful. It's very useful to understand properties. Okay? Again, the example is actually from the text, so you don't need to actually write it down, but feel free. I mean, if you want to, feel free, but I'll post them as well. Okay, so that's an example of a very, very simple case. Okay? So again, the packing density here is 68%, which is reasonably high. That's a reasonable number to expect, just so you know. Okay, we'll come back to these things later on. Again, the packing density can also determine how strong these materials are, whether they hold up to chemicals, things like that as well. Okay. Now, in crystals, we have to come up with terminology to describe crystals, because they have all kinds of geometries. Like I said, they can be very complicated. So there are 2 things we need to know to describe them. One is directions. You know, how do you describe a direction, and how do you describe a plane? Once you have these 2, then you can describe all the crystals. So we need to understand how to describe directions and planes. And historically, they're defined by 3 numbers, and they're called the Miller indices. So we need to know how to define them. So of course, a direction essentially is a vector. So those of you who've taken high school math know what vector is. It defines the direction and an amplitude, right? And a length to the vector and a direction to the vector. The direction is what we are interested in today. The plane, of course, defines a plane. 3 points define a plane. The direction can be orthogonal to the plane. We'll talk about that as well. Okay. The Miller indices have a format when they are in square brackets shown here, like HK. So three numbers define the direction and the plane. When they're in a square bracket like that, they define a direction. When they're in a regular parenthesis like that, they define a plane. Okay, so it's just a format. Now let's look at directions. To define a direction, what you need to do is draw a vector. Okay? Find the coordinates of the head of the vector, coordinates of the tail of the vector, subtract them. Just like you did in high school physics or high school math. Okay? So, and then you have to do something more, which we'll talk about in a minute. But you can see if these numbers are 1, okay, it's 1, and in the x direction, let's look at this vector. So it's 1 in the x direction, okay, 0 in the y direction, and 0 in the z direction. So it's 1, 0, 0. Okay, pretty straightforward. Or you can look at this blue vector, which is 1 in the x direction, 1 in the y direction, 1 in the z direction, 1, 1, 1. Okay? Now, of course, you can have fractions in crystals, because you will not have ones, you can have halves and 1/3 and so on. So you need to get rid of the fraction. And this is just for for notational purposes. Really has no other purpose. Okay? And you remove the fraction by basically multiplying by the smallest possible factor. So if you have half, 1, 1, you multiply everything by 2, you get 1, 2, 2. Right? We'll look at some examples. They're very straightforward. And you enclose in square brackets, you define a direction. Okay? Pretty straightforward. The planes are defined, so let's do this actually. That's an example problem. Again, do it with your partner, but let me just make an assumption. Let's assume that's halfway in between. So this is half. Okay? Because I forgot to write that down. Okay, so discuss 30 seconds.
So you just hit them.
Okay, so so what's in the x? Let's work through it. So what's ahead of the tail of the vector we know is 0, 0, 0, right? It's at the origin. So what's the head of the vector? What's the x coordinate of the head?
1.
X is 1? No. I'm talking. Let's work through the process, okay? So what is? I know you guys are very smart, but don't jump the gun. What is the coordinate here? Half. Very good. Okay. 1/2, 0, and 1. Very good. Okay. Now what do? Multiply by 2. So what's the answer?
1, 0.
Okay. Great. Now you're experts. You can do the problem sets and put it in square brackets. That's formality. Not terribly important. Okay, so conceptually, there are some very interesting things that happen for directions as well. Directions can have in crystals, you can have equivalent directions. And this is typically only true in cubic lattices where you have high order symmetry. So for instance, in a cubic lattice like this, okay, simple cubic lattice, not face-centered or body-centered, this direction is the same as this direction. Why? Because you can rotate the cube. It's rotational symmetry, right? So 101 is the same as 110. And you can, of course, come up with more symmetries. Now, these symmetries tend to be very important when you're studying properties that are direction dependent. We'll come back to these later on. And of course, they can get very complicated if you have more complicated lattices, right? Because the symmetries become complicated. They're more constrained. Yeah?
Does the origin have to stay the same to be symmetric, or can you change a different? Does the origin have to be the same to have it symmetric, or can you change the origin?
Yeah, so the origin is arbitrary, right? Remember, this whole thing is just a unit cell which is anywhere within the crystal, in any orientation you want, especially for a simple qubit. Right? It really doesn't matter. You can pick anything you want. It's an important question. It's a good question. Again, the origin can shift based on the lattice. Right? Remember, we were shifting the unit cell around, and we took one of those points as the origin. That was just a formality. It could be any of the other points as well. And any points within the lattice are equivalent to any other points within any other, unit cell. Right? They are the same. They're all the same because they're repeated. So that's why we will focus on understanding the unit cell itself. Okay? And in more complicated things like in these, in a tetragonal lattice where you can see this direction, 101 is not equal to 110 because they're different dimensions, right? One's longer than the other. So you can see the symmetry becomes important. But that's called the equivalence of directions. Okay, we do the same for a plane. Okay, the method for the plane, remember, for Miller indices, define both directions and planes. For the plane, essentially, we'll come back to the first point in a minute, because that becomes important. Essentially, what you do is you determine the intersection of the plane with the axis, XYZ axis. Now, of course, they don't need to be orthogonal XYZ axis. You can have non-orthogonal axis like we did for the rhombic lattice, right? Like we saw in that example. But in any case, in this case, if you have an intersection of 1 here in X, 1 in Y, and 1 in Z, you have a plane which is 1, 1, 1. Okay? So those are the intersections. Then you take the reciprocal of the intersection. Okay, 1 over 1 in this case is 1, so it's 1, 1, 1. You can have 1 over infinity because you can have a plane that's parallel to an axis. It doesn't intersect at all. It intersects at infinity, which means the 1 over infinity becomes 0. That's why you take the reciprocal. So you don't need to worry about infinity. And then you can convert to the smallest integers. That's not necessarily, it's again a formality. It's not important that you do it. And you enclose with parentheses. Okay? Now let's come back. So let's make sure we're clear on these 3 steps to define the plane. You look at the intersections, okay, in the 3 coordinates, so 1, 1, 1, or A, B, C, whatever. You take the reciprocals. So you have 1 over A, 1 over B, 1 over C. That's it, and you can stop. And what happens if the plane passes through the origin? You have a 0. So if you take a 1 over 0, you get infinity. You want to avoid that, right? What you do is you move by one basis vector away from the origin. Okay? Now what does that mean? Remember, if you move by one basis vector from a lattice point, it's the same lattice point. So if you take a plane which passes through the origin and shift it by one basis vector, it's the same plane as before. And then you avoided that 0. That's what the first point is saying. Okay. Do you see the problem, first of all? If you pass through 0, you get an infinite, 1 over 0, right? That's what you're trying to avoid. Anyway, so it's relatively common sense, and you will get it when you do some examples, like here. Okay? Okay, this actually, let's start with this first, because this has a negative sign. Let's do this first. So here you can see where the 201 comes from. Okay, so let's look at the X intersection. Intersection in X is, I think, is about half, right? About half. The intersection in Y is nothing, right? It's infinite. It's parallel to y-axis, right? Do you see that, first of all? That's the y-axis. That's a plane that's parallel to y-axis. There's no intersection. So it's infinite. Okay. Then the third coordinate, intersection in Z, is 1. I'm assuming it's a unit cube, 1, 1, 1. Okay? So we have intersection coordinates at half, infinity, and 1. Okay? Then you take the reverse, reciprocal of these numbers. So you have 2, 0, 1. Okay, is that clear? That's how you get the Miller indices for this plane. Let's do it for this plane. So you have half in X, 1 in Y, and half in Z. Straightforward, 2, 1, 2. Okay? Here it's interesting because it's in the negative. Let's see where the negative comes from. So you have an intersection. You can't really tell, but in X there is no intersections, right? It's parallel to X. And in Y also there is no intersection. It's parallel to Y. You see that? So 0, 0. But in Z, it's at the bottom. Okay, so the green is now the origin. So it's underneath the origin, so it's -1. Okay? When you have a minus sign, it's placed on top of the number, as shown here. So you have 1 over infinity, 1 over infinity, and 1 over -1. And the minus goes on the top. Again, just a formality. Okay? So that should be clear. And the other part, again, you can work it out. Not that difficult. Yes?
So could we have chosen to say 0, 0, 1 instead of -1 and just move our...
Yes, that's a very good point. In a simple cubic, yes, because they're equivalent planes. We're going to come to that. Not always true.
But in this case?
In this case, you can. If you don't have symmetry if you have symmetry across the origin, then plus and minus doesn't matter. They look the same. If you don't have symmetry across the origin, like we will see in some cases, you cannot do that. So the minus sign is important. Okay. So again, one important condition, property is that in a simple cubic system, if a plane and a direction have the same Miller indices, the same numbers, then we can show that they are orthogonal to each other. So basically, the plane is normal to the direction is normal to the plane. Okay, just a property in a simple cubic lattice. Okay, another example problem for the Miller index. So this is A. Got to do it here. This is A. That's 2A. That's 1, 2, 3, 4. B and 1C. Okay. Talk to your partners and tell me what the Miller indices are. Actually, I don't know the answer to this, so we'll figure it out together.
Who cares?
Also assume that A equals B equals C, so for simplicity. And cancel out all those things, yeah. Okay, 10 more seconds. Let's finish. But you should figure it out. Figuring it out is part of the process. I didn't hear you. Yes. Okay, let's do it together now. So what are the intersection points in X? 2. So 1 over 2. Okay. In Y? 4. So it's 1 over 4, and in Z is 1. Right? So 1. 1 over 2, 1 over 4, 1. You can leave it at that. That's fine. If you want, or you can multiply it through. Doesn't matter. If you multiply it through, you get, what do you get? You get 2, 1, and 4. Okay? Okay, pretty straightforward. So again, when you see problems like this, of course, the problems will be more complicated than the examples to some extent, but think along those lines. The process is what's important, not memorizing things. I don't really care. You can look up in a text. Okay. By the way, my problem sets are obviously open book because you take it home, but the quizzes, so the midterm and the finals are going to be open book as well. I really don't care. I don't need you to memorize things. It really defeats the purpose in my experience. So. Okay. So make sure you understand the process of concepts. Okay. Okay. So we have a few more things to cover. The most important lattice, it turns out, of course, is silicon, because silicon is the most common semiconductor in electronic devices. And it's based on what's called the diamond lattice. Okay? It's a bit of a complicated structure. Okay? And many semiconductors follow this lattice: silicon, germanium, carbon in the form of diamond, so that's why it's called diamond. The lattice is actually two, you can think about it in many different ways. The way I like to think about it is basically two interweaved FCC lattices, face-centered cubic lattices. So if you look here, for a moment, imagine there's only one FCC lattice, okay, which is formed by this, and that, and each of their faces. Okay, you see one, right? Ignore the other atoms. Okay, then shift them all along the diagonal by a quarter of the lattice distance. Okay, which then forms these atoms, which are shown in gray. Of course, there are atoms outside the lattice which are not shown, but you see these lattices. So this atom gets shifted up here, this atom gets shifted up here, this atom gets shifted up here, this atom gets shifted up here. Everything else shifts out of the lattice, so we're not showing it. Okay? So you have two interweaving FCC lattices which form the diamond lattice. Okay? It's a fairly complicated structure. It's hard to visualize, actually. Okay? But you can state it very simply. It's an FCC lattice with an extra atom placed at A over 4 plus B over 4 plus C over 4 from each FCC atom. That's it. But to visualize it a little more complicated. We'll look at it in a second. Okay? One easy way to look at it is if you look at it down. Okay? Instead of in 3D space, let's project it onto 2D space to understand it better. Okay? I can't visualize in 3D, so it's much easier for me to think in 2D. Okay? So if you look along 100 direction, which, now by the way, can someone tell me what 100 is now in here? So 1 is a direction, so remember it is the, what was it? I forgot now. It is the coordinate, right? So 1 in the x direction, 0 in the y, 0 in the z. So if I say this is x, I'm looking this way, right? Along the x-axis, basically. Along any of these axes, it really doesn't matter, they're symmetric. Okay, so that's what it looks like if you project all the atoms into 2D. And you can see the FCC fairly easily. So you look at all the solid atoms form one lattice of one FCC, and all the blue circles form the shifted FCC lattice. You see, this is shifted by a quarter along the diagonal. You see this as half, but remember it's projected in 3D, so that's why it's quarter. A over 4 plus B over 4 plus C over 4. Okay? There are two important forms of these kinds of lattices. The atoms can all be the same, like silicon, diamond, germanium. Or you can have two different atoms, okay, like gallium arsenide. So you can have gallium here, arsenic here. They're both important. When the atoms are different, they're called zinc blende lattices. Okay, zinc blende lattices, like gallium arsenide, gallium nitride, gallium phosphide, things like that. Okay. Again, you don't need to memorize any of this, but be aware of them. That's my goal here. Okay, so I picked out this video which actually helps you visualize the FCC, the diamond lattice. So in this case, what they're doing is basically simulating it, and they're rotating it around so you can get a picture of it with various different filling fractions and so on. So anyway, you can see that's their atom. Okay, that's the diamond lattice. Okay, you can rotate it so you can see a picture of it. Okay, this is not real because that atoms are not closely packed, right? You can see the space in between. Here, closely pack it very soon. And you can see the covalent bonds in between in this particular case. Okay, so you see the symmetries. So he's rotating it to show the different symmetries. And you're looking at different directions through the crystal. Okay. Now you have spheres representing closely packed atoms. Okay, this is more realistic, I would say. I guess this is also very simplistic, but a better picture, I'd say, than before. So you change the packing fraction, and you're looking at it to see the different symmetries. So different kinds of rotational symmetry as well, translation symmetry. Okay, you can see there are more atoms in certain directions than others, which turns out to be important. Okay, now he's removed the bonds in between, so you just have the diamond lattice we looked at. Okay, so you can look at it. Okay, let's proceed. I don't think there's anything more there. So but I have actually posted the video, so you can play around with it. Stop it, pause it, rewind it, whatever. So far we've talked about the crystal lattices, and we're going to move on. Obviously, this is a very, very preliminary discussion of the topic, and we'll come back to it as we need to. At least now you have a very basic understanding of what crystals are, how to define them, how to use the right terminology. Now the next question is, how do we make them? How do we make the crystal? It turns out to be the manufacturing is the key reason why we had the microelectronics revolution, because it had to be cheap, right? Otherwise, it wouldn't really have penetrated the market as it has. So the semiconductor industry relies heavily on crystals, primarily silicon, of very, very high purity. The purity concentration that so you can buy silicon wafers of are in the order of one impurity in 10 billion atoms of silicon. That's an incredible number if you think about it. Okay, how do you do it? And of course, we won't go into the metallurgical part, but very, very briefly, you start with the raw material, silicon dioxide, like sand. Okay, you heat it at very high temperatures with carbon. You form what's called metallurgical grade silicon, and the byproduct is carbon monoxide. It's not good for the environment, but I think they do try to capture it. Then the metallurgical silicon, of course, is not very pure. It gets purified by typically another chemical process which uses hydrochloric acid, which I won't go into much detail, but you can read in the book. It forms what's called electronic grade silicon, which is very close to the purity that one wants. Okay? Then there's a very important process which was developed by a Polish chemist named Czochralski, which produces the crystal from a molten melt. Okay? So essentially what you do is you take a very small, very, very pure crystal of silicon, which you can somehow create either by chemical methods, like small crystals can be made. Then you use that as a seed crystal in a molten silicon, so very, very hot silicon. You put the seed crystal and very slowly pull it out. Okay? And it forms, when the seed crystal touches the molten silicon, the silicon crystallizes on top of it. Okay? And that's basically what's in this video, so I will very quickly go through. It's kind of illustrative to see. So they talk about the silicon and so on, and you can watch the whole thing if you're interested. But let me... Okay, so that's the... Let me back up a little bit. Oops. Okay, so that's the Czochralski process. Essentially, you see the molten silicon there, and then you have oops. Anyway, they'll show you again in a second. Okay, so you have a furnace which heats up the silicon very, very hot. It melts here, and then you bring down a seed crystal and pull it out very, very slowly. Okay, and they'll show that soon. So it's molten now. Now, melting the silicon is useful because it can recrystallize on a seed crystal. That's the idea. Okay, so you put the seed crystal down like that, so you can see at the end it's very pure. You bring it down and it's rotated very slowly to make very uniform crystals, essentially. Okay. This is kind of a little bit didactic, but I think it's useful to see it. And you can see it's turning and it's pulling it out. So it's pulling it out very slowly, and it forms these big cylinders. They can be big. They can be 300 millimeters. Nowadays, 400 millimeters. They're huge. They pull them out like that. So this is a big cylinder of single crystal silicon. Very, very, very pure. This is a very important process that enables the industry. Okay? And this cylinder is referred to as an ingot, I-N-G-O-T, ingot. That's what it looks like. Okay? And then the silicon is actually chopped up into little wafers and then used. Okay. Okay, the result is wafers. Then, during this process, you can also add impurities. Like I showed you in the example before, we had arsenic. Antimony. It's antimony Sb, which replaced the silicon, which gave it an extra electron, if you recall, in that example. You can do that process during this pulling. So when you pull it, you can add impurities into the melt. As long as the impurity crystal structure is close to that of silicon, it'll get incorporated. And then, of course, you can control the conductivity. That's the point. Now, there's another very important method to produce single crystal structures as well, in addition to the Czochralski process that I just showed you. It's called epitaxial growth. Epitaxial growth is very straightforward. Okay? Essentially, it's the same approach. You have a seed crystal, and then you try to grow atoms on top. Okay? And the atoms are introduced in a vapor instead of having a liquid. That's the only difference. The advantage of this is that it can be extremely precise. So you can have atomic level precision. It can be done at room temperature, or much lower temperature than the melting point of silicon. It's very, very high. So you don't need to have huge furnaces and things like that. You can have a couple of different approaches. You can have vapor phase epitaxy, where the atoms or molecules are provided by a vapor. You can have liquid phase epitaxy, which can actually be grown from a melt. So the Czochralski process is a form of epitaxy. You can have molecular beam epitaxy, which is where the atoms are evaporated in a very, very high vacuum. Okay? Now, each of these processes are important for different applications. The molecular beam epitaxy, for instance, is extremely important for gallium arsenide devices, solar cells, very, very high quality solar cells, the cells that go to Mars, for instance, that power the Mars rover. They're all made with a process like epitaxial, molecular beam epitaxy. They're very expensive because they have fairly complicated systems. I'm not going to, in the interest of time, I'm not going to show you this video, but it's posted online so you can watch it. It shows you a simulation of the molecules actually form. So you can see it forms a very weak bond. So remember I told you in a crystal everything is periodic except at the boundaries. Right? At the boundaries, you lose periodicity. You take a look at a silicon wafer. At the boundary where it is open to air, there's no silicon, right? There's a layer of silicon atoms which is just looking at air. Right? So there are bonds which are sitting out, which are not attached to anything. Of course, typically you have impurities, but in the purest case, not attached to nothing. Those bonds are where the next silicon atom can fall. So you imagine a seed layer with dangling bonds. If you introduce atoms with the right conditions, it can form a single crystal layer on top. That's epitaxial growth, pretty much. And that's what the video shows, actually. So you can watch it in your own time. So essentially, the process is very simple. You have a substrate, it's a seed crystal, you have a grown crystal. And if the lattice constant of the grown crystal is the same as that of the substrate, meaning it's silicon on silicon, or, for instance, gallium arsenide on germanium, but the lattice constants are pretty much the same, then they will grow very, very high quality crystal structures, crystal layers on top. And they can be very large, lots of layers. These are important, like I mentioned, for very high-end solar cells. So this is an example of a multi-junction solar cell, okay, where you can get efficiencies as high as something like 30%, 40% or so, the world record efficiencies. Of course, they're very expensive, so you can't put them on your roof. But they are cheap enough to send to Mars or for satellites and so on, because their efficiency is more important. So, but they are grown using epitaxy, where you start with a germanium substrate, and you form a germanium cell, which we will come back to actually. Then you grow different stuff. So in this case, you have indium gallium arsenide, and this is grown by epitaxy. And then you have indium gallium phosphide, again grown by epitaxy. And these different materials allow very efficient conversion of sunlight to electricity. Okay. And this is an LED, typical structure in LED, again made with epitaxy. So you have an indium phosphide substrate, and you grow the different materials on top. Okay, you have an N-type indium gallium arsenide, indium phosphide, indium gallium arsenide, indium phosphide, and so on and so forth. These form what are called quantum wells, potential wells, which we will see on Thursday. Okay, this is a typical LED structure. Oh, I just wanted to point out, we have a company in Utah which actually sells germanium substrate. Some of you may be aware of this. These guys, Cellular, they're based in St. George. Their main product is this, germanium wafers. And these germanium wafers are used to make solar cells, for instance, or make photodetectors for the military, night vision cameras, sensors, things like that. Fairly high-end applications, actually, I'd say. Mostly military. So it's something you should be aware of. So I wanted to end today with a very brief video, but you can actually watch it yourself. So I'll stop here. This is actually a very interesting video because it gives you an overview of basically where sand becomes an integrated circuit, and it's from Intel. So it's sort of an advertisement for Intel, but I didn't mean it that way. But you can get a flow of the whole process and how what we are learning fits into the process. So I would encourage you to take a look. Okay. See you on Thursday. All the videos are posted online, and I'll also post the lecture online as well, as soon as I have it edited. Okay?